Hello and welcome to EngPhys 3004 Lecture 3, Fluid Statics. These are the problems where fluids aren't moving, so they're stationary or static. The only stress that we're going to have is the normal stress, and that's because fluids that are not moving can't have a shear stress. Remember that shear stress is the viscosity times the rate of change of shear strain. So if it's not moving, then the shear strain of the fluid is not changing with time, so there's no shear stress. Okay, so then what kind of stress do we have? We have normal stress, which is the one caused by pressure. Fluid static, you could also, in general, have surface tension, but we're going to assume for this chapter that we're at a large enough size scale that we can ignore that. The first thing that we're going to tackle is hydrostatic forces on submerged plane surfaces. So plane as in flat. What we're actually doing is three-dimensional. We're just going to look at flat surfaces first. Then we're going to look at curved surfaces later. So for now, plane surfaces. This is a cube or maybe a rectangular prism that's underwater, and it is actually made up of water. So in other words, we're going to look at some section of water and just think about what's happening to it. Now I want you to imagine for a moment why this piece doesn't fall down. It weighs something, so why doesn't it fall down? Well, it must be that there's pressure underneath pushing up on it. But wait a minute, isn't there pressure at the top pushing down as well? The only way that this can work is if the pressure isn't the same at the top and the bottom. If we find the net force in the z direction, the pressure on the bottom times the area of the bottom pushing up, minus the pressure on the top times the area of the top pushing down, minus rho g, little bit of volume of this element, the weight of the thing has to equal 0 for it to be static in equilibrium. And what that leads to is the fact that the pressure has to be changing with z given by negative rho g, or negative the specific weight of the fluid. So if we integrate this, and we can do that by taking the density as constant for an incompressible fluid, or at least constant density fluid, then the change in pressure is equal to negative gamma times the change in z coordinate. If we're looking for something that's lower, then we're looking at a more negative z, and that means that we are going to a more positive depth as we increase the pressure. To find the force acting on some wall of the flat section, all you do is integrate the pressure over the wall. And this is pretty easy when the wall is flat compared to what it's like when the wall is curved, because when it's curved, then it's a vector integral. And that's because when we say that force is equal to the integral of pressure over the area, force is actually a vector. So we really should be saying that force is equal to the integral of, well, how are we going to get a vector over here? It's not the pressure that's the vector, it's actually the area. This is just something that we can take the, we can convert into a scalar integral. If the surface is flat, then the vector part of this can just be factored out, and it only tells us what direction the force is pointing in. But if the surface is not flat, then we'd have to add up the different parts as vectors, kind of break this up into a sum of little vector elements over all the different pieces of the surface. And that is not like the integrals that you did in vector calculus before. You always had, when it was a d vector a, it was dotted with something inside, so it ended up being a scalar afterwards. This is a new kind of thing, which you know how to do in principle by thinking of an integral as adding up all the little pieces, but we don't have a way to do that analytically. So that's a hint that we're probably going to find some clever trick so that we don't actually have to do the vector integrals. All right, so pressure is often defined in terms of pressure head, which is the amount of elevation that would give that specific pressure. So a pressure head of 10 meters, if we're talking about water, is the kind of pressure that you would feel 10 meters under the water. A pressure head of 5 meters is 5 meters under the water. All the pressures at the bottom of these are the same. Why? Because they're the same height down, they're the same depth. Are the forces equal? No, force is pressure multiplied by area. So here we have one kind of force. Here there's less force on the bottom plate. Here there's a lot of force on the bottom plate. Here there's a little. Here there's a small amount. So the force is pressure multiplied by area, and this is kind of a mundane thing, but it lets you do some pretty interesting designs. This is how a hydraulic jack works, for instance. you've got a small area here that you can apply a small force to and get a big area providing a big force on the other side because the pressure at a given height is going to be equal. So how does this conserve energy? Well, the only way that you can have the work done here equaling the work done here, if this has more force, is if this side doesn't move as much. And that ends up being the case. This conserves energy for the same reason that it conserves volume of fluid. If this has less area, then it has to move a larger distance to move the same volume. And the volume of fluid that has gone down here has to be the volume that's gone up here. Okay, the textbook in this section has a lot of calculation results for the force on submerged plates. Now, as you know, the equivalent force, so if you were to find, we've got this kind of big plate here, let's figure out where the equivalent force location is in the line of action. This means the force which would produce the same torque on this plate as the actual distributed pressure force does. So as you know, the equivalent force is all well and good for figuring out what the torque on the plate would be and the net force on the plate would be, but it doesn't maintain the same picture when it comes to the effect of internal forces. So these aren't really perfect for determining whether a tank material will fail. Still, they're helpful to do some quick initial calculations short of a full simulation. Pressure varies linearly with depth, therefore the average pressure is the pressure at the centroid. To see why this is, let's just find the average pressure. Pressure average should be equal to the integral of pressure with respect to area over the area, and this is going to be equal to the integral of pressure is sort of the surface pressure plus rho g z with respect to area over the entire area. And then what do we get here? We can take out the surface pressure plus rho g, and we're going to be left with the integral of z dA over A, and that is P naught plus rho g z bar. Now this z bar, look at that, that's the z coordinate of the centroid. So this is just equal to the pressure at the centroid. And there we go. The average pressure is the pressure at the centroid. Why is that helpful? Well, because if we have a way to figure out the centroid, and that's often obvious from looking at the shape or maybe using some of the formulas that we've got down here, then you can get the resultant force by just multiplying whatever the pressure is there by the area. Okay, now where do we put this line of action? In order for it to have the equivalent resultant force, meaning that it produces the equivalent moment as the actual distributed force, then we need to have that wherever the location of it is, multiplied by the resultant force, is equal to the moment produced by the distributed force, which is the pressure dA. So using this definition, you can do some of the derivations in the book if you're super interested and come up with the calculations that it has, like this one. The equivalent resultant force using this geometry, where we've got a tilt in angle from a surface theta, theta being in this picture the angle down from the surface, y being the distance along this plate for any kind of arbitrary flat shape, we end up with the distance to the equivalent force location to produce the same moment is given by this formula, where Ixxc is the second moment of area of the plate about its centroid, as opposed to the second moment of area of the plate about the origin, O defined as this point up here in this graph. Okay, and there's a number of results in the book for second moments of area to make this a little bit easier for you to do the practice problems and calculations from. So some useful results for rectangles. Rather than use the full moment of inertia, if we substitute that result into the previous formula, then we can come up with this simplification and this further simplification if it's completely vertical. And then if it's completely horizontal, there's another formula that's useful to use, and that's this. So here we are defining where the the y's are in terms of the previous ones using this formula down here. This one works for this one and this one. For this one, the centroid is just in the middle. Now, okay, look at this one. Look at this resultant force here. Does this follow the format in the previous example? Is this a case where we could use the last formula to figure it out? Actually, no. Look at what S is in this formula. S is the distance that this side of the plate makes with wherever our origin is, and theta is the angle that's dropped down from the vertical. This horizontal plate that's just displaced a distance under the water doesn't fit into that. It doesn't work with that formula. Fortunately, you can say, wait a minute, the surface is parallel to the surface of the water, so it's all at the same depth, so it's at a constant pressure anyway. Okay, how do we actually use this? Suppose you're in a car and you need to escape it. You're in the car as shown. There's you inside. I guess it's not shown, but this is the car and it's underwater. Are you strong enough to open the door? All right, well, let's find out just how strong you would need to be. We're going to figure out what the net force is on this car door. So what are the principles we're going to need? We're going to need to know what the pressure is around here. Do we need to know the pressure everywhere on the door? Nope. We can use the trick from earlier that we just take the pressure at the centroid and then multiply that by the area, and that's the resultant force. So where is the centroid of this? Well, it's a rectangle, roughly. So the centroid is going to be in the middle, which is 0.6 down from the top, which is 8 meters down from the top. So then the pressure at the car door centroid is going to be equal to P0 at 1 atmosphere at the surface plus the rho g delta z for the depth under the water, which is P naught plus rho is about 1,000, g is about 10, and depth is 8.6. So let's just double check the units. 1,000 kilograms per meter cubed. 10, what was that? That is newtons per kilogram is G, and 8.6 meters. So then we end up with P naught plus, we've got 10,000 times 8.6. That is 86 E3 or 86 kilo, and then what are the units? Newtons per meter squared we're going to be left with. That's good. Kilopascals. Kilopascals. Great. All right. So that's the pressure that's on the outside of the door. And what we're really concerned with, because there's air inside the car, assuming that, delta P is going to be the pressure in the center minus the pressure inside, which actually is also 1 atmosphere, we're saying. So that is going to be equal to this 86 kilopascals. Okay, now what about the force? The force is equal to the delta P. This is the force we would need to apply, would be this pressure multiplied by the area. And the area is 1.2 square meters. So 86 times 1.2 is, what is that? So we got 86 plus another, the 0.2 would be like an 8, but then, so 8.6 times 2 is about a 15 on top of that. So, oh no, 8.6, that's like 17. So this would give us 86 and 17, it's like 100. So we've got 103, what? Kilonewtons. So, all right, well, do you have a good feeling for what a newton is? Maybe you do, maybe you don't. A newton is about the weight of 3 fig newtons, or about the weight of 1 egg. So this is about 103,000 eggs, or maybe 309,000 fig newtons. Fig newtons. Yeah, okay, so that is a lot of fig newtons. I don't think we are strong enough. Hydrostatic forces on submerged curved surfaces. Here's the bottom of maybe it's the side of a hot tub or something, and we want to know what the force on this part of the surface is. Now, this is going to be a vector integral because the direction of the area vector is changing all along the side of this. That's something we don't want to deal with. Here's the trick. Instead of doing that, we can just say that this force has to be balanced by the horizontal force from this side, the vertical force on the top, and the weight of a fluid element that's next to the curved surface. It's easier to add up these three vectors and find out the equivalent spot that their reaction force would be produced by setting the torque about some point equal to 0 than it is to actually do that vector integral. So that's the trick. Now, you still do have to be able to do a volume integral over this, but that's much easier than doing that integral of the vector area. Even with the trick, the practice problems here can be pretty challenging. Here's a cylinder which is attached with a hinge. It looks like a cylinder because we're looking at it from one end. And there is a water level here that when it gets up high enough, it's going to open up the gate because of the reaction force from the fluid here. So to find that reaction force, you would look at the side of it using the calculations from the last section and the bottom, same thing. Reaction force from the wall maybe, and then calculate the weight of that fluid element and where its equivalent point of action would be. Find the resultant of these three forces to figure out what the resultant force on this fluid element would be, and then the fluid's force on the cylinder would just be equal and opposite to that. The last little bit in this section is how to deal with a multi-layered fluid like this, oil sitting on top of water. Remember that we've kind of been dealing with this the whole time when we have air at atmospheric pressure on top of the surface of the fluid we were looking at. So what you do is you find the pressure at the interface, and then you just use that as your starting point to find differences in pressure as you go deeper based on the density of the fluid you're in. So the increase in pressure in the oil is based on the oil's density. You find the pressure there, and then you start from that as you increase pressure based on the water's density in water. Find the resultant force for each area separately, and then just say that they have to produce the same net torque as the total force to find out where that total force resultant should be located. The very last section for today, buoyancy and stability, is going to be for objects that are completely immersed in the fluid. And now we can do a trick where we don't have to do the calculations of the last section. So the force for something that's completely submerged, it's surrounded by fluid on all sides, it's not like a wall or anything, is going to be balancing out in all of the horizontal directions regardless of the shape, and we're only going to have a net vertical force, which we call the buoyant force. Let's look at a fluid element here. The reason the fluid in static equilibrium doesn't fall down in response to the weight we said earlier was because of the pressure difference on the top and bottom. If we integrate that whole pressure difference, the net force from that is called the buoyant force. So the buoyant force must be balancing the weight of the object, and in general, the buoyant force is an upward force which is equal in magnitude to the weight of the displaced fluid. That way it's going to balance in a fluid element, and if this solid is going to be sinking, it must be that it has more weight than the weight of the displaced fluid. So whether something's going to float really depends on the density of that thing compared to the density of the fluid. If the density is less than the fluid, it floats. If it's the same, then it can be suspended. And if it's greater, it's going to sink. This is Archimedes' principle, by the way, that the buoyant force acting up on a submerged body is equal to the weight of the fluid displaced by that body. Now, a device that takes advantage of this to measure the specific gravity of the fluid is called a hydrometer, so a calibrated lead weight at the bottom of a graduated cylinder. This is calibrated to compare the specific gravity of whatever fluid it's sitting in to the specific gravity of water. So remember that the buoyant force is based on the density of the fluid displaced, because you take that density and multiply by gravity constant and volume to find the weight of the fluid displaced, and that's the buoyant force. So if 1 is the reading that you would have in water, if you have some other fluid here, which is heavier than water, has a higher specific gravity, then it would be lifting this up because the buoyant force would be stronger. So that would You would put the indications on this dial to be higher numbers for lower readings. All right, concept question. If you put a bucket of water on a scale and then you dip your fluid mechanics textbook partly into the water so that you're still holding one end of it, but some of it's in the water, does the reading on the scale go up or down? Does the density of the book you use affect the scale reading? So basically what we're talking about is you take part of the book and you hold one end of it under the water. What happens to the reading on the scale that the bucket of water is sitting on? Everybody understand the question? Great. Moving on, stability of immersed and floating bodies. Stability of immersed bodies, i.e. surrounded by the same fluid on all sides, submerged, depends on the relative location of the center of gravity and what's called the center of buoyancy. Center of buoyancy is the centroid of the submerged portion. Let's talk about stability. This ball in the bottom of this well is stable. This ball on a flat surface is neutrally stable, and this one's unstable. This means that if it doesn't have any particular spot that it wants to sit. If you bump it, it would move a little bit, but it wouldn't accelerate away. If there's some loss of energy, it would kind of hold still in another different spot. This one is going to return back to this spot, and this one is going to move away if it gets perturbed. So same idea with stability of floating bodies. If we have a situation where the center of buoyancy is above the center of gravity, then no matter how this thing rotates, it's going to return to this position. If it's the same, it's neutrally stable, so they're coincident, then this could rotate and any position is the same. But this one, where the weight's on the top, is unstable. You can imagine if it tilts a little bit, then it's going to completely swing around. So picture this as like really floating bodies or immersed bodies. You can picture like a beach ball with one side that's heavier sitting on the surface of the water. When the weight's at the bottom, it's stable. When the weight's at the top, it's unstable. Floating bodies can be stable if the center of gravity is above the center of buoyancy, as long as they're designed so that the center of buoyancy moves if the body rotates. And this is how ships work, by the way. So for a ship like this, if we move a little bit, then the center of buoyancy will actually move to the side. So even if the center of gravity is up there, then it's still going to be stable as long as the metacenter, which is where the vertical line from the center of buoyancy meets the line through the center of gravity from before it tilted, is above the center of gravity. This distance that it is above the center of gravity is called the Metacentric Heights, and it's a measure of the stability of ships. So if the Metacentric height goes below the center of gravity, then this is bad. This ship is capsizing. It's tilted too much. Now you might think, all right, well, why don't we just put the center of gravity above the center of, or below rather, the center of buoyancy all the time, so we don't have to worry about this? And because the reason we don't do that is because then we can't ship as many things and make lots and lots of money. So do some good engineering, and you can find out ways to get much more money.